Welcome back to the next video, everybody. Today's video will be the last in the video series on chapter 5 of my notes on finite flat group schemes, and we'll finally be talking about the classification theorem and the two major theorems of Raynaud that we'll need for the proof of Fermat's last theorem. Okay, so it's a sad day, but next chapter is Langland's tunnel, so that should be fun. Okay, fundamental characters are first up, but first we need to discuss the classification theorem before we get to the actual theorems of Raynaud. And so the classification theorem is essentially the driving force behind the main results. So F here will be a finite field of characteristic P. Q equals P to the R will be the cardinality of F. Mu will be the group of Q minus first roots of unity in K bar. Okay. M will be the group of multiplicative characters of F. So it's all the maps from F star to mu. And we'll extend each chi and M to all of F just by setting chi of 0 equal to 0. Okay. If mu is in R, so remember R is a DVR of mixed characteristic under this setup. And then there are special elements chi and M called the fundamental characters. And these characters have the property that the map chi from F to R followed by the map from R to K, which is just R mod pi R, the residue field, is a homomorphism of fields. Okay. So if chi is one of these, you can get all the other fundamental characters just by taking p to the ith powers of chi, where I is at least 0 and less than R, and chi to the p to the R is chi. In other words, I mean, the upshot of all this is that the fundamental characters chi form a set indexed by what we call a principal homogeneous space, or a torsor I, for Z mod R Z, in such a way that the I plus first guy in the set is the pth power of the ith guy. So you keep taking pth powers to get the next thing in the set. And so what's a principal homogeneous space, if you've never heard that before? A principal homogeneous space X for a group G is just a set X on which G acts freely and transitively. Okay? So the classification theorem, so here's what it says. Let F mu and kind of the set of all chi sub i's for I and big I be as above, and suppose mu is in R. Then three things are true. Let the delta sub i's for I ranges throughout big I be elements of R, such that the valuations of the delta sub i's are non-negative and less than or equal to E. Recall E is VP, the absolute ramification index, and this better hold for each I. Let A be the R algebra presented by the generators X sub I for I and big I, and the relations X I to the P equals delta sub I X sub I plus 1 for I and big I. Okay. Then there is a unique F module structure on the R scheme G equals spec A, such that bracket S xi equals xi of S X sub I for each I and big I and each S and F. And with that structure, G turns out to be a Raynaud F module scheme. Okay, what is this bracket S map here? A bracket S of xi of X, let's say, is just xi of Sx. So it's basically a scale the input by S map. Okay. 2, every Raynaud F module scheme is of this type. So number 1 completely classifies Raynaud F module schemes. And then 3, suppose G and G prime are two schemes defined respectively by the equations X sub I to the P equals delta sub I X sub I plus 1, and X prime sub I to the P equals delta prime sub I X prime sub I plus 1. So they're both defined by the same equations, essentially. Then the F module scheme homomorphisms from G prime to G correspond to the R algebra homomorphisms of the form X sub I maps to A sub I X prime sub I, where the A sub i's, as I runs through big I, is just a family of elements in R, such that A sub I plus 1 delta I equals A to the P sub I delta prime sub I for all I in big I. Okay, and so this tells us how two group schemes defined by these kind of canonical equations associated to our setup in number 1 are related to each other on the level of algebras. All right, and so see it CSS page 149 for a proof of this. But this isn't somehow even the important result unless you want to know all the details. This leads to Raynaud's two big theorems that we will use. The first one is this theorem on uniqueness of prolongations. So theorem 3, we'll call it. Let R be a DVR of mixed characteristic 0P. Suppose P minus 1 is bigger than the absolute ramification index E, which remember is just V of P. Let G be a finite flat R group scheme of P power order. And then G is up to isomorphism, the unique prolongation of its generic fiber G sub K. So it's base change to K, where K, if you recall, is the field of fractions of R. Okay, and I'm actually going to give a proof of this just because I like this proof. The point is, if G isn't unique, then G plus is bigger than G minus under the ordering on prolongations, where G plus is the sup and G minus is the int. And this inequality you can check is preserved by passage to extension of R. And so what I can do is I can just assume without loss of generality by extension that R is strictly Henselian, which makes things easier. By devisage, I can even assume G is simple, okay? By proposition 7 from previous video, G plus and G minus are Raynaud F module schemes for the finite field F equals the endomorphisms of G sub K. And the reason I bumped up to a strictly Henselian R is then I know mu is an R. And so by the classification theorem part 3, if I take G prime to be G plus and G to be G minus, there have to be non-zero constants A sub I and R, such that the usual relations are satisfied. A sub I plus 1 delta I equals A to the P sub I, delta prime sub I for all I and big I. So here's what I'll do. I'll just choose I so that V of AI is maximal. And then it's easy to check using the classification theorem part 1 that E must be bigger than or equal to P minus 1 V of A sub I. But remember, P minus 1 is bigger than E, so V of A sub I must be 0 then. Well, that just means the AI are units in R, right? But that just means G is G prime, which is the claim. Okay? And so one consequence of this is the following. Let C be the category of commutative finite flat R group schemes of P power order, the ones we're focusing on here. Given two such schemes, G and H, we can form X'd GH in the category C, which is the set of all extensions of G by H and C, i.e. it's the set of all exact sequences 0 to H to E to G to 0 of elements of C. And so here's a corollary of the above theorem. It's not too hard to check this at all once you have the uniqueness of prolongation theorem. Let G and H be in C. If P minus 1 is bigger than E, then the natural map from C Homs from G to H to Galois maps from G K bar to H of K bar is bijective, actually. Okay, and so looking at kind of maps of schemes is the same as looking at maps of Galois modules. That's interesting. And the natural map of extensions in C of G by H to extension Galois module extensions of G of K bar by H of K bar is injective. So we don't get bijectivity there, but we get injective, and that's good enough for our purposes. Okay, and see CSS page 152 for a quick proof of this using the previous theorem. So what's Raynaud's second theorem? Well, the question now just becomes, given theorem 3, which K schemes G not have a prolongation? Which ones have a prolongation in the first place? And so theorem 4 answers this. Let F be a finite field with Q equals P to the R elements. Let mu be the Q minus first roots of unity in K bar, which we'll imagine as living in K. And we'll let chi sub I from F star to mu be a fundamental character. We'll let G0 be a Raynaud F module scheme over K. And we'll let phi from cal G to F star be the character giving the action of cal G, the absolute Galois group of K, on G0 of K bar. So we talked about all of this setup last video. Then G0 has a prolongation, or in other words, the representation from cal G to GL1 of F is so-called flat. If and only if there's an element which we'll call delta in K star, such that when I take any sigma in the Galois group and I look at phi of sigma, so I take the action character phi and apply it to sigma, and then I take chi sub I of that, so I apply the fundamental character to that, I just get sigma minus 1 acting on delta to the 1 over Q minus 1 power. And I also have that V of delta, the valuation of delta, is the sum from K equals 0 to R of N sub K P to the K. And again, this has to hold for all sigma in the absolute Galois group of K. And so what are these N sub Ks here? Well, they're just integers that are between 0 and E, okay? And so see CSS page 153 for a proof of this, but the conclusion is as follows. Where are we going to use these results? We're going to use them later in chapter 13. Okay, so we're on chapter 5 right now, but we're going to apply this theorem in the case R is ZP, the p-adic integers, and G naught is a simple P power, is a simple group scheme of P power order. Okay, so that's the setup we're going to apply these to. All right, so that's the end of chapter 5. We're at the end of an era here. Next chapter, chapter 6 of my notes, will be a discussion on the Langland's tunnel theorem and the point in the proof of Fermat's last theorem where it is used. So I will see you all tomorrow, and thanks for watching.